Very brief welcome. My name is Laura Bartolo. I'm at Northwestern University, and I'm a co-chair of the Materials Data Interest Group. We also have Gretchen Green from NIST in the US and Daniela Hassan from Aachen University in Germany, and they represent the co-chairs of the engineering interest group. So it's a joint session, very full, as you can see from this listening here. We're going to hold all of our questions till the end, and we're also asking each of the speakers to introduce themselves. So I will now turn this over to Ben Long at NIST, who will start us off.
Thank you, Laura. Hi, everyone. My name's Benjamin Long. Sorry, just one quick note. I think this is on auto advance. I don't know if there's a way to stop that. Oh, thank you so much. Excuse us 1 second. All right. Oh, looks like, okay. So whoever comes up, manage the auto advance. One more?
Put it in this mode.
Okay, perfect. Thank you, everyone. I'm Ben Long from NIST, and my role today is to, so we have to manually advance this. Okay. Sorry, folks. So my role today is I'm simply going to give an overview slide to introduce all of the lovely work you're going to hear about today. And honestly, what this slide is it's really a big picture view of what you're going to hear today that will introduce several really exciting presentations. Each presenter is going to give you different aspects of some things that you may or may not have heard about, but you'll hear uniquely in this context. Be it ontology development, lab information management systems, large language models, and more. We want to call your attention to the idea that behind all of these in their work and likely in aspects of yours is something universal that's always present. It's a life cycle. And in fact, it's actually two intertwined life cycles. And at the top, what you see is the cycle of how knowledge grows. It's kind of a wonderful thing. We all deal with it, but we don't always think about how knowledge grows. And whether you're the scientist that's facing the phenomenon directly and you're being very empirical about it, watching how events follow themselves in space and time, gathering data, or if you're a second or third order person doing data science, trying to assemble this knowledge together into general principles and then apply it. We both fit into this life cycle in different ways. And from that knowledge, whether we're developing it for science or applications, we eventually use tools. And when we engineer tools, it turns out the engineering process is a knowledge development process too. And that's what it means to gather requirements and build complex systems that help us do data science. And so whether it's a large language model, or it's a lab information management system, or it's higher order infrastructure that fits together, all of these things intertwine. And so as you hear each presentation, think about not only how the presenter stuff fits into the life cycle of knowledge, but maybe yours. And so with that, just trying to, we have a few sessions coming up. You'll hear from June Lau from NIST first. And following that, we'll hear from Gerhard Goldbeck about ontologies, followed by Josh Talon. Felix Engel, TIB Terminology Services, will come after that, followed by some updates on large language models from KG Schmidt, University of Chicago. Laura Bartolo and company will follow with moderation and questions. So we'll hold those to the end, as she said. And then Gerard will follow with a final update. So thank you very much. June Lau, please come and join us. Thank you, June.
And how do I advance the slides?
Roll down.
Oh, I have to at the bar?
Yeah.
That's the only way to do it. Okay, thank you. Thank you. Well, good afternoon, everyone. I am Jun Lau from NIST, and let's hopefully we don't have any slide mishaps. So first, I want to say, I want to actually acknowledge and thank Ben Long here. Due to a recent death in the family, he put this entire slide deck together for me. So I wouldn't be here without him. So thank you so much, Ben. All right. So this is, I'll talk about LIMS later on, but I want to update everyone on what we've been doing since the last meeting in Gothenburg. So I'm not really going to go into what LIMS is because I think a lot of us knows what that is, but instead I want to do a small introduction. So of course I work from the NIST side, right? So in Gothenburg, we talked a little bit about this LIMS to LIMS, and that was with Hank Burkholz and also Dave Albert. I don't see Dave, but and then Ben, right? There's like a group of us that worked on a little bit like communication between LIMS. But since then, I also wanted to introduce a couple of colleagues from BAM that we've since worked with, and they're actually in the audience. So I'm going to ask you to direct all of the ontology questions to Marcus and Bern over there in the audience, and then Hank couldn't be with us today. So here we go. I'm going to skip to the next slide. So my BAM colleagues over there have developed an ontology for material science and engineering, and it's called the PMDCO, and they have published extensively on this. And what it is that it's as they explained it to me, it's a mid-level ontology that describes a lot of the concepts in material science and the relationship and how they're related. And if you think about material science, you could think like underneath there maybe you could group things by the material classes, say metallurgy, polymer, ceramic, so forth. You could talk about like the techniques that you use to look at that material. So for example, analytical instruments, beamline, X-ray, but the NIST work is focused on electron microscopy. And so for example, going back to the PMDCO work, they have this material science mid-layer ontology here, and they have really done a very nice job in filling out the relationship with all these other material. And I know they have quite a bit of a metallurgy background. And so some of these boxes may be really, really well filled out, but not so much for electron microscopy. So we met and they say, hey, what do you know about electron microscopy? So at NIST, we have an electron microscopy LIMS. And we also had been working on vocabulary for electron microscopy. And this is based on some work that we've done with yet another NIST colleague, Alden Dima. And we had used natural language processing on a corpus of conference proceeding from the microscopy and microanalysis conference that spanned 20 years from, I think, 2001 to like 2019, and there's some gap years. And then what we did was we took this NLP work, we extracted, like 1,000 or whatever it is most commonly occurring terms, and what they are. And what we did was I had sent this list to the PMDCO folks over there, and what they were able to do. And so this was all computer assisted work. And with this, you can see my cursor, right? So this is NIST work down here. And what we did was we were able to plug into their ontology under electron microscopy. And in a really rapid fashion, we were able to get to a lower level ontology relationships and terms in a pretty rapid fashion. Now, this is not to say that this was a once and done, right? This required domain expert, right? In the cycle, we need to iterate over this a few times. But we were kind of impressed by how quickly we were able to do this, and not to suggest that we were 100% right, we're not, but we got to maybe 70% right, which is I think pretty good. So you could see what I did here, right? So this is what the NIST small contribution to their larger ontology space. You could imagine that we could do a similar, maybe even using like large language model, we could kind of complete these other boxes that may be missing in a really rather rapid fashion. So we wrote a little white paper, a little manifesto on what it is that we want to do. If you're curious or want to read it, I'd be happy to share it with you. We could talk afterwards. But so I think yeah, so I think the point is here we bring back the LIMS, right? So LIMS is, the way I think about LIMS is really at the bench level. This is we're trying to manage content that's being created from the laboratory, whether it is from analytical instrument or maybe you're doing compute, right? The LIMS is really what's feeding the knowledge upwards. So you could imagine that this echoes a little bit closer to some of the LIMS to LIMS work from the previous, except maybe what the realization that we had was maybe the communication level isn't at the LIMS to LIMS level. Perhaps it should be coordinated elsewhere, perhaps at the higher level. So we had a little toy model, right? Let's just say we want to build something that's a little bit bigger than LIMS at this point. We want to say we want to support discovery of science. So we put together a toy query. So for example, we asked ourselves, what is the relationship between, say, for example, A, conductivity, and say the angle of your grain boundary in say metals, right? And so that is represented by this little white square here. So for example, if you query it, it goes into the ontology, it looks for those relationships, and then somehow the ontology will magically call upon the LIMS and say, pull up and serve up all of the laboratory information that is going to substantiate that query and give me some answer, right or not, but this is the toy model that we would like to build. And so you imagine that here's the piece A, right? Piece B and piece C from whatever your LIMS may be. You can serve that all up, and then it could give the scientist some satisfactory answer. All right, so this I'm ending. So LIMS, my work, it's way down here in my opinion. Lives very close to the places where data is generated. And then I think of the people who do ontology and knowledge graphs, they're kind of like really way up there in the level of abstraction. And I think what we're missing right now is some middle layer, right? Some clever way to coordinate all of those LIMS activities. And so this is kind of where I will end, and would really like to have some collaboration. Come talk to us. We really want to build this. We're missing some pieces. We're aware of it. The two take home. So Gerhard has the MO, although I'm given to understand is maybe more physics ontology. Here's the PMDCO, right? And you have all of these trenches under all of these disciplines. And what we learned is two things. One, it could be very fast now with the technology to develop to fill in those trenches, but that at the end of the day, your LIMS are all the way down here. They're the worker ants. They want to bring up the information, but what's missing is how. So with that, I will end. Thank you so much for your attention.
Thank you so much. Let me see. The next one should be. What's it? 1 second. Ah, okay. I need to. Is it in? No. Will be also. Oh yeah, yeah. And then I can also do this. Should be all right. Yeah. Okay, thank you. Thank you so much. Oh, hang on. There was an auto.
Is it auto advancing? Just
Let me see. Maybe, hopefully, yeah. No, it's.
Sorry, just do it in this mode.
Yeah, let's keep it that way. And oh, okay. So I have to have the page down somewhere. Okay, well managed. So sorry about the technical things. So what I'm going to do is in the next few slides, just update on some multiple regional activities in the ontology space and also metadata space. It's really metadata and semantic artifacts and so on. And we already, in fact, had the first part of that. And I will also include something which is great to have the people here from BAM that could surely answer some questions. I'm starting with something from a previous RDA at the RDA 18. This is about activities in Japan, and there are many activities ongoing, but the points I wanted to say here is what emphasize here from that presentation. It's about sharing well-defined data schema, yeah? And there are some examples here, and wouldn't it be nice to have more of those? And the other approach there is you have a particular case, and then you develop the developing schema for that. So it's a sort of a bottom-up approach. And what we also see, there are also kind of more top-down approaches. In fact, if we go to developments that are taking place in Korea at the Materials Data Station of Korea, there's the establishment of a materials data standard. One of the authors is Kwang-Ro Lee. He's registered, maybe he may be online as well. Probably would be quite late for them at the moment. What this is about is a kind of materials, metadata schema that can describe all sorts of complex material systems and experiments about them. So it's not an ontology, but it's a designed to be available and be able to deal with a very large range of cases. It has a common vocabulary for the different methods, so let's say analysis methods, as a vocabulary for materials processes, and keyword formats that include value, uncertainty, measurement conditions, and so on. So it's meant to be both very practical and also usable across many different applications. So these are sort of metadata and metadata schema approaches. Then if we go now to Germany, these slides here were I'm grateful to Pedro Dolabella Portela from the platform Material Digital for providing these slides. And again, I showed just some snapshots here. There is a large number of projects in the phase 1. This is only the first phase of 3, I think. There are 53 different institutes and 13 different projects. And these projects typically develop ontologies for their applications, but in a network approach. And this circle is showing that. And then we already heard the PMD core ontologies, which is one of the sort of key core developments for providing a semantic interoperability. There are meetings as shown here to that. And again, I can't say a lot about that, but it's great to have some people in the room who could, if there are any questions. So it's a kind of a different approach, right, to what we're seeing here. It's an ontology-based approach, an ontology network-based approach. Then we have in a number of European projects, the EMMA ontology, the elementary multi-perspective material ontology, about which I know a little bit more about because I'm also one of the co-authors of that. This is really a development to say, okay, we need to have a top-level ontology framework that works for applied sciences. So in philosophical term, it's what we call a nominalist ontology, i.e. it only describes things that are real, that really kind of exist. It's not really about sort of abstract things like thoughts or something like that, other than, you know, the way in which it is physically sort of instantiated. It is based on merio-causality, which is a new fundamental theory as well, which will be published soon based on existing, you know, analytical philosophical principles, and is also based on the standard model. So everything physical is really somehow made up by the standard model, because that's our current understanding. So that's at the very, very high level. But then, you know, you can express things in different perspectives. So things like data, or, you know, a book, you can say the book is basically about the data, or you can say the book is an object, or you can say the book is a material, right? So the perspectives are a key part of MO. And then at the middle level, you have these things like that are sort of whole disciplines, typically references like metrology, units, workflows, and so on, these types of things. And there is now basically the whole of QDT integrated in MO. And then at the domain level, very large developments, in particular in the battery area in Europe, in European projects like BigMap, and also in characterization, in crystallography, and so on. And also, you know, general standards like DCAT, Schema being integrated also in MO as well. So it is basically a foundation on which projects can build. Then there's been the OntoCommons project, and I also have a poster on that, if you want to hear more about that, where we say, okay, we have many ontologies in material sciences, but what's the landscape of it? And how can we make them interoperable? And so there is a work on, first of all, surveying them, and you see a number of different top-level ontologies being used, and then a number of ontologies, for example, from the US, also nanomine, materials mine, and then in other ontologies across different fields. But really, what we see there is both the field is not really extremely well covered. So what we heard earlier in terms of, okay, we need to fill all of these things, maybe even using large language models, what June was saying, to populate actually the domains, because they're not that well populated at the moment. That's one thing we need to do. And we need to do this bridging, because people do different ontologies, and somehow we need to map and bridge between them. There's been other sessions discussing that also. There will be Birds of a Feather session tomorrow on that. So this is this bridge concept. I won't go into that. That is basically one kind of formalized, templated way of guiding people to say, okay, how does this term relate in that ontology relate to kind of related term in another ontology? And it's sort of, yeah, it's a guided process of doing that. And one thing we have, for example, applied that to have like a taxonomy of physical matter, where, for example, a material is a more general thing than a chemical substance. Also, actually, in current usage, often materials are kind of classified as a type of chemical substance. But if you look in detail, it isn't. Finally, the Czech developments, that's just 1 minute. I think for Marek, who will talk to that.
Yes.
Even 2 minutes.
Thank you very much. I'm Marek Cebeca from Herovsky Institute, Czech Academy of Sciences, and I'm representing here a Czech community of material scientists and engineers. And why I'm here is to indicate that we are actually building a new system, new repository, and we are learning from all the developments presented here. And I just indicated in this schema that we need these ontologies relatively with a certain level of granularity. We need also to define physical samples, instruments. We need to verify data within a Czech platform. And of course, this will be integrated with European systems. And so just to indicate that this will be a test bed for the developments of, for example, PMDSO or EMMO. We will have a look, how does that work in a real life with the users at the end. I know in NFDI, this is to some extent working, but there are already existing some systems, so that limits you, whereas we can really take a fresh step in and connect, for example, the Korean model with the ontologies which are being developed throughout the world. Thank you very much.
Okay. For congregations, it's always important.
All right, thanks everyone. My name is Josh Taylor, and I come to you from NIST, the Office of Data and Informatics. I work closely with Gretchen and June. I'll be presenting a less technical effort and more of an introduction to some work that we are doing trying to build community understanding about LIMS in the United States. Standard NIST disclaimer, if I say anything, it's not an endorsement. This effort is being funded through the National Science Foundation Materials Research Coordination Network. This was run through Duke and Northwestern universities. And their primary goals are to convene the community, to develop metadata standards and shared tooling to enable really fair materials research, and to connect the efforts of critical stakeholders in material science and engineering research to support national goals for the United States. So some of their initial efforts to this point, they hosted some jointly hosted virtual seminars back in December of last year. The first one was Microscopy and Fair Data by Mitchell Taheri from Johns Hopkins University. And then June, who we have with us today, gave a presentation about electron microscopy facility data management using Nexus LIMS. Another primary activity that this Markin, I don't know if that's how you pronounce it. Martian? Okay, that makes, now the logo makes sense. Okay, I get it. Martian has convened 2 working groups. These are a 1.5 year, 18-month efforts, one in microscopy and one in LIMS, and I'll be talking to you about the LIMS one today. These are working groups consisting of recognized leaders in the United States in these areas, and have had face-to-face meetings throughout this year, and had a meeting actually bringing in microscopy vendors as well, trying to get them involved in the conversation. That's a viewpoint that is often missing when we get these efforts sorted together. So we've had some meetings with vendors as well. The microscopy metadata working group is, I'm just going to point out the co-chairs, and apologies that the formatting got a little wonky here. Mitra, Ed Bernard, and Maria Chan are co-chairing the microscopy metadata working group, and they're really looking at in-depth what metadata do we want our microscopes to produce for us, and can we recommend some sort of common structure for that. I'm coming to you from the other side, the LIMS working group. I'm co-chairing that group along with Eric Stock from the University of Pennsylvania. And we're more looking at, okay, what do we want out of LIMS in the materials science and engineering research community? So our working group, we call it the Fair LIMS Data Working Group. We are trying to bring together, or we are bringing together, nationwide experts in material science and engineering from across academia, government, and industry, including microscopy vendors. And our primary aim is to make recommendations that will facilitate the use of LIMS in actual materials research and engineering in the labs. So this is a very low level sort of effort, going back to June's little diagram there. LIMS is really close to the research data, and that's where we're trying to live with this working group. So we have kind of four main goals. We really want to document what are the best what are best practices for recording experimental metadata and materials analysis, both on the research side and on materials engineering. We would like to foster awareness of existing recognized schemas in this area. A lot of materials researchers are starting to learn a bit more about metadata and why it's important, but there's still not really broad acceptance of why that might be in the materials research community. So we really want to foster awareness of these things. We also want to identify, if any, key gaps in these existing schemas and the current methods that we use, if any, to record metadata in materials research practices, and document how the use of a LIMS in materials research can really benefit not only individuals doing the research, but also institutions and the wider community as a whole, by better structuring our data. We're going to try to deliver a few things in this effort. This is still sort of an introduction slide, so we don't really have any deliverables to share with you at this moment, but we will be documenting the various capabilities that are required to implement a LIMS at your institution. And we'll be doing this from the perspective of various stakeholders, both from the individual level all the way to perhaps a large institution level. So we want to be able to tell people what will they need if they want to implement a LIMS. We'll be delivering a description of the value that you get if you were to implement a LIMS, along with what that might cost you as an individual or at your institution. And again, from the perspective of various stakeholders. We will provide a review of existing metadata practices in material science and the cognate disciplines with references and links to those where applicable. And we want to deliver a document that is easily digestible by a material science researcher, not necessarily someone who is embedded in a community like RDA, right? That may not know a lot about metadata to begin with. We want to make this digestible for sort of in the trenches materials researchers. And we want to, if possible, develop and publish or recommend an extensible schema that is appropriate for use in LIMS, so that can be that can facilitate the sharing of information in a LIMS to LIMS type structure. So we've divvied up our working group into sorry, I wasn't sure how much time I had, into 3 main areas. These have been decided based on basically our members' primary interests. So these 3 areas are sort of the values and costs of a LIMS, the capabilities that you must have at your institution to enable a LIMS, and then sort of in the more technical aspect of the work is the LIMS schema. What sort of metadata should I collect in a LIMS? And that will be a review of existing metadata strategies and perhaps development of another if that is applicable. The subgroups will be working independently and periodically reporting back as a larger group. And the outputs of each of these groups will be collected into a set of recommendations that we can put forth as a working group that represents at least this subset of the materials research community. Again, targeting people who are in the trenches of materials research as opposed to people who are very familiar with metadata strategies. So here's just a kind of high-level overview of our progress thus far and our expected timeline. As I mentioned, this is about a 1.5-year effort. The working groups were convened in May of this year. So we found at the beginning of this year, the members were identified and a draft proposal was put together. We had our sort of initial meetings in May. Working groups met at Northwestern University to sort of hammer out the working group proposals and what we expected our outcomes to be. So that's kind of what I've presented to you thus far today. Recently, just a few weeks ago, we brought in a variety of instrument manufacturers and vendor representatives to both gather feedback from them, what is important to them, what would they like to get out of an effort like this, but also brought a number of them on board onto the working groups themselves, which provides a really important perspective from people who actually have to solve these problems with regards to, okay, what metadata do I need to collect to make my instrument functional? So that provides a really important perspective that we're excited to have on these working groups. Going forward from here, throughout now to say the first few months of next year, it will be preparing our draft recommendations, really getting in, buckling down and working in our subgroups to prepare these draft recommendations. And then starting in the spring of next year through the fall of the year after, through the fall of 2024, we'll be presenting these recommendations at various meetings, such as the Materials Research Data Alliance annual meeting, I believe is in February, and other venues that materials researchers often attend. And we'll be gathering feedback at these meetings from the community in order to incorporate that feedback into our final recommendations. And then we hope to publish those final recommendations in the fall of next year, most likely in a materials research journal to try to really get access to the materials research community where they are, published in a place where they actually look for scientific progress. So that's all I had. I think I am 1 minute ahead. So thank you.
How does it work? Okay, very good. Yeah, hello, welcome. My name is Felix Engel. I'm from Germany, Hannover, National Library of Science and Technology, and I want to speak about the terminology service and some experiments or experience that we have made in the NFDI for ING initiative, which is actually a project within a huge initiative. It was mentioned, NFDI was mentioned previously, so you may all know what the NFDI is about. A huge research infrastructure project that we work in Germany on, and actually it considers many research disciplines as the engineering domain or the cultural domain or the chemistry and so forth. Which is quite interesting to see the different needs within these different disciplines. The terminology service actually is a service offered to manage and to provide access to ontologies in the engineering domain. And we faced lots of problems actually in the initial phase, and we still have. Because other than in the life science, where ontologies are really well established, in engineering, at least that's my experience, it is not that much the case. It's a kind of a initial phase. There are some established ontology, but rare, but in comparison, at least to the medical domain or to the life science, rather rarely. And it's always really interesting to look in the life science to see how they create ontologies and how they manage ontologies, what workflows they have established, and what active communities they have to work and maintain such ontologies. And I think this is something, at least for the engineering domain, that we really could see as a really nice blueprint for our work. And I would really like to emphasize that the work with ontologies is a collaborative one, and it is something that has to come from the community and has to be really actively maintained by a community, so that it can live even a funding period has finalized. Actually, we have heard lots of ontology creation initiatives that work on further ontologies, and I rather have sometimes the fear that these ontologies live for a certain time period, but after or when there is not enough resources available, there is at least the risk that such ontologies disappear, and that is something that we would like to address with our terminology service. And here I have some, I think, important key characteristics that ontologies are really domain specific. Yeah, we have really clear defined ontologies for the chemistry, for the cultural domain, and name them. But even within there, you find communities with different views on and definition of concepts. So it's really a broad range that you have to consider when working on ontologies. And the second point is that ontologies are quite dynamic. There's never a version, at least in how I see it, where one can say that's the final version. That's it. I mean, somehow ontologies reflect our human thinking and how we perceive certain concepts and how they are interrelating, and this change over time. So I think there's never a final version of an ontology. And then, so that's something that I mentioned previously, that if ontologies does not have a strong community behind it, we we risk to work or to create work that is in isolation, because if ontologies are created only to kind of share an understanding within an organization or within a department, let's say, yeah, then we have an isolated solution for that department, for that very limited circle. But in my understanding, ontologies are not specifically made or available to work on a common understanding, yeah, an agreed understanding. So we have to align, we have to go out. We should align with existing definition as much as possible. And this is really something that ensures that your ontology, even if you have no further funding to work and maintain your ontologies, to keep it alive. And my focus here is on the engineering terminology service, and something that we call Sandbox, which is a quite new development, which introduces some new features that we are working on. But here is a screenshot for on our terminology service, the engineering domain. Actually, at TIB, we have several terminology service, one for the engineering domain, one for the chemistry, and we even have a general terminology service that holds loads of ontologies from various domains. We had, as I said, many. It was a challenge to find those ontologies for engineering and domain. We now have more than 90 ontologies available in the service. Some of them are kind of really new. They are not what I think well established, but they seem to have some importance. So we added them, and well, maybe that's just an explanation. We add those ontologies that seems to be relevant for a given user. So we get feedback from users, and we add those ontologies that we are asked to add, because we think this is a community effort. So what we get from the engineering domain, we try to include. But we have some criteria of those ontologies that we add. That is, they must have an open license. They must have a license, and the license must be open. Otherwise, we are not able to process those ontologies. And they have to pass some quality checks. So we validate our ontologies again, certain criteria. And we, the service itself, it offers some free text search for ontologies in the engineering domain, but even within, so you can search for concepts and relations and stuff like that. You can browse and filter for ontologies. You can visualize them. We display many metadata that goes along with those ontologies. And we even have a REST interface that's rather technical, but it allows application developers to query our service and to to get all the information that are somehow encoded in the ontologies to be incorporated in their applications. So now, quickly, this is the Sandbox. That's part of the terminology service. And here we introduce some new tools. And what we actually want is to bring those tools out. We want to show them to the community, and we would really love to get feedback on it, how the community thinks that such tools are useful, or how they can be adapted or further developed, and the like. One of the tools that we have available in the Sandbox is mapping. mapping was mentioned previously. One of the very, very important aspects in ontology development, because this really allows you to align with existing definitions, with existing ontologies. And that's something really critical, to get out of an isolated solution, but to be more open and integrated, so that you can use your ontology really much to communicate across barriers. Yeah, not within your scope, but across barriers. That's something really critical, I think. And briefly, we have as well a web protege tool that is an extension of the existing tool. We host it. It is deployed on one of our TIB servers. And what it actually does, it integrates a Git functionality. So that was missing previously. So that you, from your Git repository, where you hopefully manage your ontologies, fetch the ontology collaboratively with a web protege, edit your ontology, and push it back to Git, everything within this web protege tools. And we have plenty more tools, but I will skip them here. I say thanks a lot for your attention. We have a poster tonight. We would love if you come around, and then we can discuss everything. And that's it. Thanks.
So for our next speaker, we have KJ Schmidt at University of Chicago. And she's going to be presenting remotely. So I'm not, and she will be moving, she will be able to be seen. We will be able to view. Yeah, KJ, good. And her slides.
Okay, my slides up in presentation view. Okay, can you all see my slides okay?
Very well.
Oh, great. Okay, well, I just lost my notes, so let me find those again. And there we go. Okay. So my name is KJ Schmidt. I'm a research scientist at the University of Chicago and Argonne National Lab, and I'll be talking today about LLMs for schema and ontological uses. So first things first, what is an LLM? So LLM stands for large language model. And this is a type of machine learning model that's designed to perform natural language processing, or NLP, tasks. So LLMs require a huge text data set, which is also called a corpus, for training, and they require a lot of computation power to run. So LLMs are trained on text, and these words are represented as vectors in a multidimensional space. And that multidimensional space, I have a picture on the right that just shows 2 dimensions, but just imagine hundreds of dimensions in this space. Each word is a vector in this space, and they're grouped together in different ways in these different dimensions. So this is how LLMs calculate the probability of the next word. So I just want to emphasize, they don't actually know anything. It's all about the probability of the next word in the embedding space. So LLMs, they do these NLP tasks. These tasks include text generation, question answering, text or document classification, summarization, and more. These are just to get you started thinking about what LLMs can do. So do you have experience with LLMs? Probably, even if you think you don't. So you may have seen and even interacted with an LLM through ChatGPT. That's from OpenAI. I know it's gotten a lot of attention recently. You may have experienced through predictive text. If any of you have an iPhone and you use iMessage, it's got those like 3 words that it suggests at the bottom when you're texting. That's predictive text. Or in your email, if anyone uses Gmail, when you go to reply to an email, a lot of times it'll have those automated responses at the bottom that somehow sort of match the tone of what you were going to say anyways. So that's an LLM. Customer service chatbots, if you've ever gotten in a loop with one of those. And then also in other ways that you may not have realized, unfortunately. So this is a screenshot of Twitter, someone messaging another user about like meeting up for coffee, and the other user is an LLM. They're like, I don't have a physical entity, so sorry, can't do that. But yeah, so LLMs for applications for schemas and ontologies. So here are just like a few high level ideas. On the left is the idea, and then on the right is what that prompt might look like to an LLM. So the first idea is you can use an LLM to bridge between existing schemas, and that prompt might look like, here's schema A, here's schema B, create a schema that accommodates both. We could also convert to different formats, and that prompt might look like, convert this JSON into a Python object. And you can also use it to speak to APIs natively. So you can say, write an API call to Globus that pulls down the latest data for this query. And I would say on this third one, a lot of times it's a great place to start, but may not be totally correct, but still it's a great place to get started with your API call. So more specifically for LLM applications in materials and chemistry, we actually, we as in my fellow organizers on this slide, Ben Blazik, Kevin Jablanka, Andrew White, and Ari Skortas, we actually hosted a hackathon for LLMs in materials and chemistry this past spring. So we had international participation. 192 people participated in some way, and we ended up having 14 team submissions with other teams that had projects in the works and just weren't ready to submit. So a lot of really cool things came out of this. I have a bunch of screenshots there on the right, but I wanted to highlight 3 projects that I thought really were great applications for schemas and ontologies in materials and chemistry. So this first project is extracting structured data from free-form organic synthesis text. So this is an application that formats unstructured text for describing organic synthesis procedures into JSON. So it uses plain text from the Open Reaction database and an LLM from OpenAI, and it extracts free text components and formats them into valid JSON. So a model like this can significantly increase the data that's available for training models on tasks, such as predicting reaction conditions and yields. You can find out more about this project. I've got the GitHub information below, so you can see the username and the repo name. And also they post a thread on Twitter about their project too, which you can find if you look up their username. The next project I wanted to highlight is called Insight Graph, a visual journey through materials articles. So this is an application that uses LLMs and data visualization to create materials knowledge graphs, as you can see on in that screenshot on the right. So it prompts an LLM with an example JSON containing a high-level schema with information on possible entities and pairwise relationships. And then this model returns a knowledge graph representation of the entities and their relationships. This one has a really cool video on Twitter if you look up Daphne on Twitter, but you can also find this repo again on GitHub. But this is really cool. You can use different paper, you can use like multiple papers or just one paper and create these great knowledge graphs from them. And my last project I want to highlight is called Table to JSON. So this is structured information from tables in scientific papers. It's an application that converts table information in papers into JSON. It prompts an LLM with a desired JSON schema and the HTML of a table contained in a scientific paper. and generate structured JSON with the data in the table. So this application enables automated data analysis, extraction, and integration into computational workflows right from the paper that you're reading. So this one also has, so it's got the GitHub repo, but it also has a website that you can go to, and it may take a moment to get up and running if someone hasn't used it in a while, but you can very easily go and test this out. It's very cool. But yeah, so the biggest takeaway from these hackathon projects is that these LLM applications are continuing to grow. They have such great potential for the scientific community. And there are so many software tools that people can use to get LLMs up and running really quickly in their workflow. So your dreams of using an LLM for schemas and ontologies in materials and chemistry can be a reality. So for more information about the hackathon projects, we actually published a paper after the hackathon. It's called 14 Examples of How LLMs Can Transform Materials Science and Chemistry, a reflection on large language model, on a large language model hackathon. So it features all of these submissions in more detail. And the paper is actually also featured on the podcast that I have a screenshot of on this slide, called the Materialism Podcast. It's episode 75. You can also look up Ben Blazek on Twitter. He's my group leader. He has a pinned thread on his Twitter page that has all of the hackathon submissions with a little description above each one. A lot of the submissions have videos that show how to use them, which are just really cool to see the full workflow. Yeah, so thank you.
So KJ, hope you would stay on so that we can see you. And at this point, we have time for questions from you. We've really tried to lay out a large block of time so that there can be questions, discussions. We're hoping not only the audience would be asking questions, but perhaps the presenters themselves may have questions for one another based on what they've heard. So at this point, I think if you had a question, raise your hand and someone will come around with a microphone. Oh, and we have a question in the back. Do we have any questions? No.
Hi, thanks for a really interesting talk. This is for the last speaker. It's actually from my colleague because I snapped him a picture of your table to JSON slide, and he asked me how they're using the DaVinci work, how are they using DaVinci in the workflow for that? So I said I'd ask for him.
You know what? I did not make that project, so let me go back to my slide. So it they give it the desired JSON schema, and then they give it the HTML of the table that is contained in the scientific paper. And yeah, they're using text DaVinci 003 from OpenAI. If he has more questions about it, look up the paper. I can put the paper in the, or I'll put it in the shared notes. So you can look it up. It's got more details, and it also has a link to their GitHub repo, so he can see exactly the code they're using to put that in their workflow. Sorry, I don't have the specifics to walk you through it.
KJ, I put the link to the collaborative notes in the chat, if you can see it.
Perfect. Yeah, I'll
and
put
I
that
think,
in there.
Yeah, there's some notes down at the bottom from your talk.
Gerhard, there's.
Oh, you can just go after.
Yeah, I have a question for Felix. I mean, very much like this, what you're developing there. This is really what we need. But the issue on other tools is often that it requires the developers of ontologies and terminologies to actually submit their ontologies, terminologies to, let's say, the portals, right? I mean, there's also industry portal now in the OntoCommons that does sort of similar things. How do you deal with that? I mean, it seems like you are actually ingesting from your side, because this is on a practical level, you know, I think a very important point.
Yeah. Fine? Yeah, now, right? Yeah, so actually we discussed this. We have seen from Bioportal perspective, they allow ontology uploads by the authors, right? And I think that's quite good because with this way, you really engage those people, and because sometimes there are versions of ontologies that we can't properly pass, and if you know, then we just reject them. We may write them an email if that ontology is really much important, but if the authors of those ontologies are more engaged in that portal, I think I would say it's a plus. I have no experience with it because we do it differently. But I think it's good. However, we decided, and this decision is as well technically based, because our base system is ontology lookup system. Yeah, and this system does not allow any user management, and actually it is made in that way that the software or the service maintainers, or TIB in our case, have to take care about those ontologies. And well, yeah, it works good for us, but yeah, it for sure provides work for us. Yeah.
This is a question for KJ again. This is in relation to that maybe table to JSON paper, but just a kind of more general question. In my limited experience with LLMs, they will often confidently say things that don't necessarily exist. And so if we're using LLMs in a framework like that, where say, hey, you know, hi LLM, this is a paper, please extract all the information out of it. I'm curious, just on your perspective of how do we do validation that it's returning what was actually there? You know what I'm kind of asking is it giving us is it confidently giving us garbage and then we're getting garbage into our analysis pipeline, or is there some way that we can kind of test against it?
Okay, so for the projects that are doing like taking something from this format to this format, you know, given the information, it's usually pretty good at, it doesn't make stuff up when you give it the information, they just put it into this format. So that's really nice. So for things like that, it's pretty accurate. And people are, but I would say in terms of actual like automated validation, we don't have that. You know, these were smaller scale projects. People are looking at it and saying like, oh yeah, this makes sense and I can use this and this is the information. I know that the first project that I highlighted that uses the ORD database, taking that free form text and putting it into JSON, they actually did have some sort of validation. And they said it was 93% accurate. So yeah, I think that's a really good question, because LLMs love making stuff up, and you know, it's all about that vector space and you know, like what's closest to it and you know, where the probability is the highest for the next word. But so far for formatting things, it's really good at being able to take information and just put it into a different format when you give it the information.
I have a question for all the speakers. Could you comment on definitions that go alongside your terms and whether or not you have them? In some of the other RDA sessions, they gave the example of a bond as a term. And one definition from one ontology is a financial instrument that is designed to secure an agent's debt for the holders of that debt. And specifically on the terminology service, I searched for a bond and found 93 examples. Have you looked at having a machine take a look at all the different entries for bond and try to make sense of that?
Yeah. Yeah, actually that's the thing with ontologies, right? There are so many ontologies out. I mean, look for agent or system. Yeah, you will find really many definitions of them, and they are all true in the scope of that ontology, hopefully, but not outside of it. And therefore, I think a mapping is a quite important tool, so that if we say that the agent or the bond in my ontology is the same bond in that other ontology, so we can have this connection, and then we talk about the same things, and that's quite important to distinguish if that label and its the definition true in a certain in your context. Yeah.
Just say something about you know, from the Onto Commons MO and so on perspective. I mean, first of all, in Onto Commons we have the bridge concept, which is not called the bridge term. So it's and also in MO, you know, we typically talk about concepts. If you talk especially to Emanuele Ghidini, who's really the lead author, he's like a bit of a concept purist in the sense that all of the classes do not have a URI or IRI. Well, that has a name in it. So it's just a hexadecimal string, which, you know, is also a bit impractical, but it also means that what you're defining here is a certain concept and not something that is known by a certain name. But in general, yeah, I mean, we really have to be aware of that and always have very strong elucidations and usually not what we call definitions, because again, a definition would be you could actually axiomatically define something, but you can only really ever, I mean, there are very few things you can really define. Most things you can just elucidate.
So I think at this point, we can close this presentation session, and we were also going to have Gerhard come back and give a discussion or lead a discussion on a new working group within RDA that he and others are co-chairing. So if we could go back to the slides. Well, they're not displaying. There we go.
Yeah, so what we are discussing, and also got the support from the RDA Tiger Scheme for, is to set up a new working group. And the background is really that the creation of a coherent and semantically annotated, as we just discussed, terminology and then also ontologies for material science and related domains is very much needed to underpin fair data. And also, as we have seen, there are nationally and internationally a lot of activities now and have been over the past years. So it's also, from that perspective, an opportunity to bring together all of these activities, utilize also already existing RDA recommendations from other groups, in particular vocabulary, metadata, and so on, and make that into a system that kind of works on a practical level for material sciences. And we've seen the example, and we are also hoping to use that as a use case that Marek presented, a community in you know, of researchers in Czechia and so on. So we're also collaborating, obviously, also internationally, and how, you know, what should they do? But we have many other cases as well here.
Maybe just check to see if people are familiar with what Tiger is, just because you introduced that so that they understand.
So the not the best person to introduce RDA Tiger, but I'll try. But the RDA Tiger scheme is really a scheme to support working groups both in terms of the setup of the working group and also I think then running working groups and so on in order to make sure, you know, we get the case statement and work in terms of RDA recommendations. And this has been extremely helpful for us so far. We've applied to that scheme to help us actually in the setup of the working group, and that's been great so far. But Gretchen can.
Oh, I just wanted to share because some people here may be familiar with Tiger. And it is a group formed through EOSC, the European Open Science Cloud, to help, as you explained. And it will help for RDA. It does not represent it is not a RDA like governing body. It is from EOSC, but it is open to different regions and different groups that are all participating in RDA. There's going to be a similar group that's going to be formed in RDA US called Tiger Russ. That's going to, because these working groups are challenging to identify what your goals and objectives and deliverables are going to be. So kudos to you for reaching out to Tiger. It's, you know, they're really, you know, very helpful for people more broadly. So I'm just sharing that because besides this specific session today, it's just something for other people to be aware of if you're interested in these supportive services that are working closely with RDA.
Yeah, thank you for that further explanation. And yeah, I mean, we're working with Ryan O'Connor, who's been, as I said, extremely helpful with that. What we're at the moment, so there is a link also at the bottom here, where I already set up that working group so that people can actually join it, although it's still at the pre-approval stage. We have a case statement which we are, honing and you get some details that we're working on. The objectives of the group are also shown here. It's about collecting and reviewing existing vocabularies and terminology schemas for the material science and cognate domains such as chemistry. Again, we can, on that point, already draw on and would like to draw on, of course, the collection activities that have already been happening and are happening. Then we would like to propose and verify best practices for material science practitioners to achieve fair data based on terminology schemas and ontologies, and identify needs for harmonization of terminologies and schema in the material sciences, and demonstrate successful implementation of fair terminology schema and ontologies in specific use cases that we've just discussed. Here are current co-chairs. So we have, we are, fortunate to have a representation from different regions, and the potential output is that review that I mentioned, the recommendations for how to apply the FAIR principles in the domain, the documentation of material science terms, in particular to support wide reuse, bridging, and crosswalks, and widely shared chemistry materials resource for terminologies, metadata, schema, and taxonomies. So this is again making recommendations, not making a new resource in terms of also point 4 of instantiation, but again, what are the existing resources that we would recommend for usage? One point on that I think will also be very important is to come up at least with some recommendations on a high-level material science schema. We've seen the one from Korea, which is obviously a candidate. But even without going into all of the details that represents, that could be obviously a specific, a schema for applications. But if you go to a higher level of annotating material science data and data sets with some context, and there have been many sessions, we are now entering into the world of going beyond, let's say, DCAT and Schema that represent the digital object into the domain context. What we have there is the situation that, for example, in schema.org, there are no there are no properties or so you could actually use for the material science. There are now some in the chemistry area, but not in material sciences. So again, that tends to lead to bad practice of materials being labeled as chemical substances, although they are actually something that is a bit different. Or, materials being, there are some metadata for that relate to a material in a product and so on, which again, is kind of related, but not, a material is not immediately in a product. So again, the absence of those schema are a bit detrimental at the moment. There's also, for example, as I said in another session, if you look at the linked open data, there is nothing on materials, which is probably not because there are no materials data, but if there are no metadata, then there are no data in the linked open data set. So making a little bit of an inroad in that direction is what we would like to achieve. But also it is not that easy when you, we have to think about, what does it mean to set up a working group, right? We're not launching a 3-year project. We're launching a working group, which is supposed to be 18 months, is quite focused. So hence the trimming aspect. So how do we go from the wish list to something which is really focused enough to be achievable in an international effort and with international agreement in that time frame? That's where we are at the moment, but hopefully we'll conclude that very soon and submit that. But any feedback would be, of course, extremely welcome. Thank you.
Any questions or comments for Gerhard about the new working group?
How would you like people to express interest in participating?
So first of all, of course, I've made the link to an actual working group so that you can actually join the working group that way. That gets you on the mailing list. That way we can discuss further. And therefore, there you also see the current case statement and the points that I've just talked about in a bit more detail. And what I would like to hear is comments about, of course, any comment is useful, but in particular, amongst the things that we are saying, what is the highest priority for you? What should be the focus for? What are things where you say, well, that's kind of already, maybe of lesser importance, maybe already done, maybe, so prioritization is really the key at the moment, I would say.
And so where you would sign up is on the RDA site?
Yeah, on the RDA site, I've got the link here, and I think you should say it. But on the RDA site, you would also obviously find it by looking for the working groups.
I think it's right down.
So it's under groups, harmonized terminologies and schemas, fair data, material science.
It's still at the proposed phase, right?
At the proposed phase, but the link is on the RDA side.
Okay.
So that'll be put in the collaborative notes if people are interested in following up and potentially joining if it becomes.
Yeah, I'll put it. Oh, I can put it in as well. Yeah. Mm-hmm.
Yeah.
Okay. Good. So we have actually finished a few minutes early, which I don't think probably is a problem for most people at the end of the day. But let's thank our presenters. They all stayed on time. We covered a lot of ground and they were very interesting talks as well.
Which wouldn't have happened without your organization, all right, I have to say.
Right. Good. And good evening to all. Thank you so much for taking those notes.